Alright, this video is intended for those who have watched my videos on effective nuclear charge, ionization energies part 1 and part 2, and electron affinity. In this video we're going to talk about the characteristics of metals and nonmetals. We've been talking about how metals tend to have low ionization energies and low electron affinities, and that's why they lend themselves to forming positive ions. And nonmetals have high ionization energies and high electron affinities, and that's why they tend to be negative ions. So in this video we first want to distinguish the difference between metals and nonmetals, and hopefully you've seen a periodic table and you know where that stair step is that starts from boron and goes downward. That separates the metals to the left and the nonmetals to the right. And because we have that line that separates the two, there must be distinguishing differences in characteristics between the two. So here they are. Metals, what you need to know about metals is metals tend to have delocalized electrons, especially the transition metals. So what that means is that if each one of these positive charges represents the nucleus, the electrons are delocalized, which means the electrons from this particular atom could flow over here or here or here. They can freely move between the nuclei of different atoms of the metal. So you say, well, what's the implication of that? What these delocalized electrons, what does that do for me? Well, it makes them malleable and ductile. I can hammer these out into thin sheets, so the nuclei can move around. We can hammer them out into thin sheets. We can polish them. They're shiny. Think of gold, silver, copper. Can be polished. They're good conductors of heat and electricity. I can put an electromotive force on this end of a metal wire, and the electrons will be pushed pushed off these last metals and outward like this. So there's a force that pushes the electrons, and that force translates all the way to the end until the electron pops out the other end. So because of that, they're good conductors of heat and electricity. If you've ever cooked with the metal spoon, left it in a pot of boiling water, come back 10 minutes later, the spoon's as hot as the boiling water is, whereas a wooden spoon doesn't do that. We've talked about that they have low ionization energies because of a low Z effective. The effective nuclear charge is low compared to nonmetals. So if you haven't seen the video on effective nuclear charge, you may want to do that. They tend to form ionic compounds with chlorines. We've seen sodium chloride. Sodium forms positive one ion and chlorine forms a negative one ion, and that creates an ionic bond between them. And then here's one that's important later on. They tend to form metal oxides, and these metal oxides, when added to water, tend to form basic solutions. So important later on, maybe not so important at this moment. So nonmetals must be quite a bit different, otherwise we couldn't distinguish between the two. So nonmetals generally are not shiny. If we think of a piece of charcoal, which is mostly carbon, much different than a metal. You hammer on a piece of charcoal, it doesn't hammer out into a thin sheet. It tends to just break apart into little pieces. Again, nonmetals do not have those delocalized electrons that we think of with metals, and that's one of the characteristics that really defines these two properties. Also defines this property as well, that they are poor conductors of heat and electricity. So metals tend to be good conductors of heat and electricity. Nonmetals tend to be poor conductors. But that's a good thing too. I mean, that's why you cook with a wooden spoon. That's why you insulate your house with a mostly carbon-based fiberglass insulation. Nonmetals as nonmetal oxides, they tend to, when dissolved in water, to form acids. Like carbon dioxide dissolved in water can form carbonic acid. So nonmetal oxides tend to form acidic solutions. And just as sodium has a very low electron affinity, that's why it doesn't form a negative ion very easily. Chlorine, being a nonmetal, having a high Z effective of +7, for easily gains an electron. So chlorine is a gaseous atom, gains an electron, and releases energy, called electron affinity. So if you haven't watched my video on electron affinity, you would want to watch that before you continue on. Now, there are some elements that they are in touch with the stair step that separates the metals and the nonmetals. They're called metalloids. They tend to have properties of both metals and nonmetals. And generally what they have is, when we look at the atomic scale, or very small wires on the atomic scale made with nonmetals, they tend to conduct electricity like a metal, but they also still tend to be brittle like a nonmetal. So those are called metalloids. They have properties of both metals and nonmetals. And they generally touch the stair step that divides the metals and the nonmetals, except for aluminum. All right, so we're going to talk about ion formation in the D block, or what causes. So we've talked about ionization energy. Metals tend to have low ionization energies. Nonmetals tend to have high electron affinities, which makes them negative ions. So we want to talk about why that happens, or what is going on here. And so one of the things we're going to talk about is elements gaining or losing electrons to become isoelectronic with a noble gas. So we know noble gases, we saw that they don't want to gain an electron because that extra electron has to go up in another energy level. And they don't really want to lose an electron because they have a high Z effective of 8 positive, and so it's hard to remove an electron from a noble gas. So noble gases are at the low of an energy well. They are typically, because they're of a lower energy, they tend to they tend to be stable. We used to call the noble gases the inert gases. We didn't think they would react. We know that they can react under certain conditions, so we call them noble gases. So the other elements on the periodic table will tend to gain or lose electrons and become like a noble gas as far as the electron configuration goes. So hopefully you've watched the video on electron configuration. So here we're going to show how metals and nonmetals gain or lose electrons to become like a noble gas in electron configuration. And instead of saying like a noble gas in electron configuration, we say it's isoelectronic with a noble gas. So here is our electron configuration for sodium. And again, very easily atomic diagram, 11 protons for sodium. And 2 electrons in the first shell, 8 in the second, and 1 in the third. So there's the 2 in the first shell, there's my 8 electrons in the second shell, and there's 1 in the third. And so sodium, having a low ionization energy, loses its outer shell electron. That electron goes away. Ionization energy 1. And we're left with this. So we've lost a shell. So now what we have is we have a sodium cation with 2 electrons in the first shell and 8 electrons in the second shell. Now, sodium doesn't lose any more electrons, and we talked about that with successive ionization energies like ionization energy 2, 3, and so forth. So if you haven't watched the video on ionization energy, especially part 2, that would be important here. So notice that if you look at this electron configuration, it looks a lot like the noble gas neon. So neon has a 1s2, 2s2, 2p6 electron configuration. Or if you'd like to see an atomic diagram, it's neon, 10 protons, 2 in the first shell, and 8 in the second shell. Now, some students get confused. A sodium ion is just like neon. No, it's not. Neon is neutral. Neon does not have the same effective nuclear charge because sodium now is 11 protons in the nucleus minus the 2 core electrons. So it has a Z effective of 9 positive. Whereas neon has 10 electrons in the nucleus minus 2, so it's 10 minus the 2 core electrons. It has a Z effective of 8 positive. Sodium is a charged ion, neon is neutral, so don't tell me that neon and sodium ions are exactly the same. All that's the same here is they have the same electron configuration. So we look at chlorine. Chlorine, this is its electron configuration, 3s2, 3p5. There's 7 electrons in the outer shell. So if we, again, 17 protons, 2 in the first shell, 8 in the second shell, and 7 in the outer shell. Chlorine being in group 17 should have 7 electrons in the outer shell. Chlorine has a high electron affinity, so it gains an extra electron, becomes a negative ion called an anion. So this is called the chloride ion. And that's how we distinguish it between chlorine and chloride. So chlorine is not something you want to breathe. It reacts with the moisture in your lungs and forms hydrochloric acid. But you swallow chloride every day in the form of table salt. So totally different chemical properties between an atom and its ion. Sodium burns underwater. You can only smother it with sand or a special fire extinguisher, but sodium ions you swallow every day. It's the other component of table salt. Totally different properties. So if we look at this electron configuration for chlorine, what we would find is that it has the same electron configuration as argon. 1s2, 2s2, 2p6, 3s2, 3p6. So instead of saying it has the same electron configuration as argon, we just say chlorine is isoelectronic with argon. Just like up here, we said the sodium ion is isoelectronic with neon. And you go, well, why do I need to know this? So part of it is you need to know that sodium forms a positive 1 ion, chlorine forms a negative 1 ion. They're both isoelectronic with noble gases. That's going to help you compare ion sizes to neutral atom sizes, because if they're both isoelectronic, then with like argon, or both were isoelectronic with neon, then I can definitely compare the size of those two based on what the charge is on the ion. So that's where we're going with this. Now, you're not really comparing these two directly in that this is sodium's isoelectronic with neon, chloride ion's isoelectronic with argon, but you should be able to see then that sodium, because it lost a shell, is a very small ion compared to sodium that still has 1 electron in its outer shell. And chlorine, when it gains the electron, that last electron is not attracted to the nucleus very strongly because the Z effective hasn't changed. The core remains the same, and the number of electrons, the electrons in the inner shell up here, up to this, to 2p6, is the same. So that last electron that we added to chlorine to make it chloride is not attracted to the nucleus, so the chloride ion is larger than the chlorine atom, whereas the sodium ion is much smaller than the sodium atom. So that's what they're showing here using abbreviated or noble gas core, and you can see that sodium with its 1s electron, 3s electron, 3s1 electron, loses that outer shell electron, becomes isoelectronic with neon. Here's chlorine. It's got 5 electrons in the p sublevel, gains an extra electron in the p sublevel, becomes isoelectronic with argon. So you should be able to write the electron configurations for each of these ions. All right, so you may want to stop the video at this point and see if you can write the electron configurations for each of these ions, or you could write the noble gas core electron configurations. That'd be a little easier, wouldn't it? All right, so try that. All right, welcome back. So right off the bat, you should go, oh, neon. Neon's in group, it's in period 2. It's in group 15. What's to gain 3 electrons, become like the noble gas neon. And so that's what this is. Nitrogen becomes neon. Nitrogen is going to have the same electron configuration as neon. Barium. Barium is in group group 6. It's going to lose 2 electrons. It's going to become isoelectronic with xenon. And then beryllium being in group period 2. Yeah, I think I said group here. It should be period 5. Period 5 for barium. So period 2 for beryllium loses 2 electrons and becomes isoelectronic with helium. All right. So very easy, very quick. Again, negative ions, anions, positive ions called cations. There's a loss of electrons here to make positive ions. There's a gain of 3 electrons here to become an anion. All right, and there's our solutions that we've already come up with. All right, this is the one that causes students the most trouble, and I really want you to focus on this one because I find most students miss this even after talking about it, and it's really important that you understand what happens in ion formation in the D block. So we're in the transition metals, groups 3 through 12, and we already have asked you in class to memorize that iron comes in a 2 positive form and iron comes in a 3 positive form. And we said that was polyvalent. All right. So we just told you to memorize it. And you probably were like, why do I need to memorize this? Or I don't want to know, just memorize it. I want to know what is happening. We're now at a point we can explain why iron comes in a 2 positive form and a 3 positive form. So the first thing that you need to know when you form a positive ion is that you are removing electrons. The second thing you need to know in order to do this correctly is we always remove from the highest principal quantum number shell and then work our way inward. So you never remove from the 3rd energy level if there's electrons in the 4th energy level. So you always remove from the highest principal quantum shell. So when we look at iron, we can see this has a higher principal quantum number than this, which makes sense. This is the 4s2, and the periodic table tells you that we fill up the 4s2 before we go back into the 3d. So what happens is students look at this and they go, well, this is on the outer, they look at that and go, that's at the end. So they want to remove these 2 electrons to make the iron 2 positive. It does not work that way. You always remove from the highest principal quantum number first. 4 is greater than 3. So when we go to remove 2 electrons, it is the 4s that are removed first. These 2 electrons from the 4s are removed first. Now let's look at that like an orbital diagram just to show you what's going on here. The 4s is here and the 3d is up here. And the 3d has 6 electrons in it. Again, Hund's rule says put them in parallel spin first, then go back in pair. So that's what iron looks like. This is iron. Now, these are higher in energy. I agree with that. But the principal quantum number, this is the outer shell. not this. This is the 3D up here. So the first two electrons removed are from the highest principal quantum level, and that's the 4th quantum level, and that's how we get iron 2 positive. Now, we have electron-electron repulsion here, so it's easy to remove this 3rd electron from iron, and that's how we get iron 3 positive. So we remove the 4s2 electrons first, and then we remove one of the electrons from the 3D, and we get iron 3 positive. So iron 2 positive, we remove the 4th energy shell first electrons because it's furthest from the nucleus. It is the outer shell. It is the highest principal quantum level. And then we start to remove from the 3D. All right. So let's have you try one. Let's have you look at, write the electron configurations for copper 1 positive and copper 2 positive. All right, so this is how you would start this. I would start with copper, and I would write, just to make it faster, I would use the noble gas core. So argon was the last noble gas crossed on the periodic table trying to get to copper. So there's argon. Then we have the 4s2 and the 3d9. Now, those of you that have really studied electron configuration, you're going, that's not the electron configuration for copper. The electron configuration for copper is argon, 4s1, 3d10. And you are correct. That is the correct electron configuration. When we talked about electron configuration, and we're using the numbering system of 1 through 18 for the group numbers, we see anomalies that occur in group 6 and group 11. So group 6 is like chromium, that's what's in the 3D, and then group 11 is copper. So this is the correct electron configuration for copper, 4s1, 3d10. And you go, why is that so important? Well, now you can see why copper forms a positive 1 ion and a positive 2 ion. So we remove from the outer shell first. There's 1 electron in the 4s. So copper 1 positive is going to be argon, 3d10. All right. And copper 2 is going to be argon. We remove the 4s1, and now what we have is 3d. We remove 1 from the 3d, and we get 3d9. Oops, 3d9. So again, what I find most students do, they look at this, they want to remove the first electron from here, they want to remove the 2 electrons from here. That is incorrect. You always remove from the highest principal quantum number first. You say, well, how am I going to know that for sure? Well, if you need a mnemonic or something to help you out here, one of the things you can do is you can go, okay, copper has 29 protons. All right? It's got 4 shells around it. It's got 2 in the first. It's got 8 in the second. It's got, if you go with this, you would have 18. You'd have the 8 that you went through the first time you went through period 3 plus the 10 here, and you have 1 in the 4th. All right, so 10 plus 18 is 28, plus 1 is 29. And now you can easily see this electron has to be removed first, this one, which is the 4s1. So if you'll do that, you won't make the mistake. The main thing here is to write this out on paper and look at it before you make a decision. And that would be for any ion formation. Write it out. Either use an atomic diagram or do the electron configuration. But write it out. Don't do it in your head. If you'll do that, you won't make that mistake. And I guarantee you, you're going to be tested on ion formation of a D block metal sometime in your general college chemistry course. Hope that helps. Thank you.